Okay, so I need to share my screen, I suppose. Okay. Yeah, can you see it?
Whiteboard.
Whiteboard, yeah. Okay. Very nice. So, what I will talk about. I will talk about a polynomial. From a manifold with a torus boundary. Okay. So I'm sorry for my handwriting because like it is only the beginning of the lockdown and I lost my skill to write good, though I use a special device. Okay, so if something is not clear to you, please ask me. Okay, so what is the thing? So the main thing is a polynomial. What is it? It is a polynomial in two complex variables. My talk will be organized as follows: that I will like introduce the main players, and then I'll say something maybe about the proofs of some statements, because like I'm really new to this subject, less than a week for the familiarization. Okay, so let's go. A of Lm is a polynomial in two complex variables. So from what setting do we start? We start with M. M is a, say, orientable three manifold with a toric boundary. Yeah, but the main example is when we have a complement to a knot in S3. So we have a three-dimensional sphere, and we just throw out some epsilon neighborhood of a knot. Okay, so we like have something like this. We take a small neighborhood, so the knot should be, of course, what is called tame. Yeah, not a wild knot. That some small neighborhood is properly embedded into our S3 space. I'm sorry, someone's microphone is on. Okay, so let's go. Then yeah, and then the boundary of our M is of course a torus. Yeah, and what is important for our construction that in the boundary of M we have the special we can choose special representatives of first homologies. Okay, so we all know that.
Sorry,
Yeah.
let me comment. Значит, А-многочлен – это некоторый инвариант трехмерных многообразий. Я правильно понимаю, что речь всегда идет о трехмерном, да?
Yeah, so we start, да, мы начинаем с трехмерного многообразия, дальше мы сейчас некоторую конструкцию придумаем, ну, не придумаем, изложим, и получится многочлен от двух комплексных переменных.
Значит, в этом трехмерном многообразии мы можем рассмотреть узел, одномерную кривую, связанную. И вот Саша говорит про то, что главный пример – это узел просто в трехмерной сфере, в обычной трехмерной сфере, самые обычные узлы, которые мы рассматриваем на нашем семинаре. И таким образом, конструируя инвариант многообразий, мы на самом деле конструируем инвариант узла. Если мы взяли узел, узел – это завязанная окружность как-то, и утолщили, рассмотрели эпсилон окрестность этой завязанной окружности, при маленьком эпсилон, то окружность становится полноторием.
Без границы, да.
Полноторием. Ну, да. Вот. И ну, мне предпочтительнее смотреть на него как на полноторие с границей. Можем рассмотреть замкнутую эпсилон окрестность. Вот. Окружность становится полноторием, граница это полнотория – это тор. И когда мы полноторие выкидываем из нашего многообразия, например, из сферы, то то, что остается ориентируемое трехмерное многообразие, граница которого – это тор. Поэтому, если у нас удастся построить какие-то инварианты таких многообразий, вот там многочлен – это инвариант таких многообразий, он одновременно становится и инвариантом узлов в трехмерной сфере. Окей.
Yes, so it was mentioned that we look at a knot in M, but it is like to be more precise, we want M to be like we don't want to have knots in M with like toric boundary. We want to have like arbitrary manifolds with toric boundary. For example, the ones which are complements to a knot over some closed manifolds. So we have a closed manifold and we throw out a knot from it and we obtain a manifold with a toric boundary. Yeah, okay. So let's go further. Yeah, what we need further is that to discuss the pi1 of the boundary. So pi1 of the boundary, of course, is z squared. Yeah, because it is the fundamental group of a torus, and we need for the further constructions we need to choose the generators in this Z2. And for an arbitrary manifold, we need to specify the generators. But for a complement to a knot, we have a specific representatives. Okay, so we fix the generators of dm of pi1 dm for this our specific setting of particular interest to our seminar and both to the authors of the paper. We fix L and M, longitude and meridian. So what is a meridian? So if you look at a knot close at a knot. It is just some neighborhood. It is just an interval. Yeah, and our solid torus is like this. Its section is like this, and we can have we say that this is okay. I need to we go around this solid torus, and we say that it is a meridian. Okay, so M capital. Yeah, and longitude goes along the knot, and L goes along the knot. Yeah, but if we have we go arbitrary along the knot. Say we start. Okay, I need a color again. One moment. Okay, so we started here. We want to go along the knot, but then we may do some rotations. Yeah, when we go along the meridian. Yeah, and we need somehow to say what representatives of this long curve do we want. And we say that we want the one which is not linked with the original knot and not linked with K. Yeah. Where? Okay. And not linked with K. Yeah, so we have the two generators in the fundamental group, which is the same as the first homology group of a boundary torus of our three-dimensional manifold. Okay, so now let's move on. So we'll go to new paper. Okay, new page. Sorry, what do we do next? So we want to study the manifold, the knot, in the terms of representations of the fundamental group of our manifold and of its boundary. Okay, so we'll need some definitions.
Sorry, just a short comment, a brief comment in Russian. Значит, если наша торическая граница нашего трехмерного многообразия – это эпсилон-окрестность дополнения, эпсилон-окрестность узла некоторого, то в этой торической границе мы можем выделить с точностью до гомотопии, как это нужно переводить, longitude meridian, meridian это меридиан, наверное, на торе.
Да,
а longitude это...
Долгота, широта, по-моему, да? Широта, да.
Ну, широта, но как-то она плохо смотрится. Ну, в общем, плохо смотрится в этом контексте. Важно, что есть два выделенных цикла. Один – это вот наш старый узел, который сердцевинка этого выкинутого тора. Вот от него остается след на наружности тора. И это будет один цикл. Он обматывает тор один раз в одном направлении. А второй цикл – это маленькая окружность, которая обходит, мы берем точку, берем ее эпсилон-окрестность И тогда это граница этой эпсилон окрестности – это сфера, и вот экватор этой сферы, мы выбираем какое-нибудь направление, в котором мы обходим этот экватор, он дает второй цикл. Вот у нас есть два выделенных цикла, которые называются L и M. Обычно, если у нас есть там, целочисленная решетка Z2, у нас нет никакого разумного способа выбрать базис однозначно в этой решетке, но разных базисов много. Ну вот в этой конкретной ситуации такая возможность есть, и Саша планирует этим пользоваться.
Yeah, and thank you for talking about orientation. I forgot to mention what we can here fix also. So about the orientation, we of course we can when we have a knot, we can say that when we go the longitude goes into the same direction as the knot goes. Yes, so if the knot is oriented like this, so the longitude could be also oriented. And then about meridian, we can also orient it. But in arbitrary case, when we have just a toric boundary, what we really need will be the pair of two generators up to simultaneous change of their orientations. And why can we do this when we have a complement to a non-oriented knot? Because we can say, look, the manifold is oriented. Yes, yes. Then the boundary is also oriented, because like external normal, you know. So that this torus, boundary torus, is also oriented. And then if we orient somehow one of we orient somehow longitude, and then the meridian, we should orient it in this way that here we will have like let's draw it. We'll have longitude meridian. We'll have then the longitude which goes like this, and they intersect in some point, in the point where we took a base point. Yeah, pi1 should be like pi1 dms comma x0. Yeah, x0 base point. So this is x0, and then we can draw the velocity vectors. Yeah, and they should form a positively oriented basis in the boundary. In the boundary torus. Okay, so if you just have a non-oriented knot, we'll have longitude and meridian up to the change of sign, simultaneous change of sign. Okay, so L and M are defined. Up to simultaneous sign change in additive notation. Okay. Okay, so now we'll go further. So now they're like the main flavor of an article is algebraic geometrical. So what we do here, we have some like manifold. We have some M, and then R. M is a manifold, not only the original one, but some. So R of M is a variety of SL2 C representations of its fundamental group. Yeah. Okay, again, some base point, but the fundamental groups will be isomorphic when we change the point. So, yeah, M, of course, is some good manifold connected, etc. Then x of M is a variety of characters.
One should say characters.
Characters, okay. Again, of SL2C representations. By one of them. Okay, so characters are just character of representation on an element of group.
Before telling what is a character, please tell us what is a representation.
Okay. Okay. Okay, so a representation is a homomorphism from the group that we study into the fixed group. Here we have SL2C, but generally speaking, a little, just not for the record, just we group X on something. Yeah, and here, where do we act when we are in SL2C? We act on C squared, but we act not arbitrary. Arbitrary will be we need to be in GL to C, but we act only by the matrices with determinant 1, so we preserve the volume. Okay, so a representation of a representation, say rho, from G okay, I think it is, I can say this is a homomorphism. Okay, so from the G to SL2C. Then on each element, it maps an element to a matrix with a with a determinant 1, and then a character of a representation. So on G it is again a map from group to SL2C. So on G it equals trace of rho of G. Yeah, okay, so like this. Yeah, so let's go further. What
I hope Sasha will be back in a few minutes.
I'm sorry, I just I was out, sorry. Okay, oh, it is all, everything is cleared. Sorry, but when where did I stop when you last time heard me?
You were defining what is a representation.
Yeah, and did I define what the character is?
No, not.
No. Okay, sorry. Okay, so representation. Of group in TSL to C is a homomorphism. Okay, so well, let's say like this. From homomorphism from G again to SL to C. So a character of representation. So it is again from G to SL to C, or from G but not to SL to C, but just to C. So on the element of G, it is a trace of row of G. Okay. Yeah. So then we want to say how we use it in our construction.
Sorry, Sash, before you proceed, Misha, can you comment on this character variety, character manifold? Do you hear me? No. Okay, then proceed. We do not have comments from Misha Shapiro's side.
Yeah, I was the most part of my preparation for this talk was like reading about some algebraic geometry, because like it seems to be fairly like straightforward, just representation character, but we somehow look at it as at a variety, yeah, and then we at some point we resolve singularities. At some points we take irreducible components. Yeah, so definitely we need to say something if we need to be rigorous. But I think that for to say that it is like from topological point of view, we just take like the space of all SL2 C matrices, like the topology is given by topology of matrix where matrix entries are like local coordinates, and in this space we have a section like we have a surface which is not surface but how it say hypersurface, yes, that is defined by the equation that the determinant of our matrix is 1. Yeah, and then we have, if we have a group, we take its generators, we look at what is the, like, how, what is the image, what is their image. Yeah, and this gives us the information about the whole representation. Yeah, somehow this is what we really need. But of course, yeah, there are some like thin things there. Okay, so let's go further. What we really need, we take our manifold. So let's just, I think, so I'll draw. I'll say, well, okay, we have M, we have dm equals 1 crosses 1. We have L and M fixed generators of H1 of dm to simultaneous change of signs. Okay, so and then we look at R diagonal of dm. So what is it? It is a variety of diagonal representations of the fundamental group, the same as homology group, of the boundary torus. Representations of H1 of dm. Okay, so it is given by the images of L and M. So rho diagonal of L will be, if we have L here, then here we have the inverse, and when we look at the image of M, okay, again we have M, 0, 0, the inverse element.
Okay, let me comment. Those probably in Russian and in. Значит, у нас есть две разные группы. Ну, фундаментальная группа или две разные группы первых гомологий. Это вот, давайте я буду говорить о фундаментальных группах.
Да, речь про них.
Речь про них, да? Значит, у нас есть фундаментальная группа границы нашего многообразия, то есть фундаментальная группа Тора. И есть фундаментальная группа самого многообразия. Фундаментальную группу Тора мы знаем очень хорошо. Значит, это решетка размерности 2, двумерная решетка. И вот мы знаем у нее образующие L и M. И мы знаем еще, кроме того, что есть отображение фундаментальной группы границы в фундаментальную группу многообразия. Значит, при этом это отображение вовсе не обязано быть вложением. У него может быть нетривиальное ядро. Например, если наш узел – это просто незавязанная окружность, то дополнение к его эпсилон-окрестности – это полнотория, а у полнотория фундаментальная группа S1 просто. Фундаментальная группа окружности, поэтому там не может быть двух независимых. Сейчас в полнотория фундаментальная группа Z, поэтому там не может быть двух независимых элементов. А L и M независимые элементы в группе, фундаментальной группе Тора. Вот. И, Саш, что утверждается? Верно ли, что во всяком представлении фундаментальной группы многообразия в SL2 от C элементы L и M должны быть диагональны?
Нет, это не утверждается. Это просто
Это
вот
не
берется
утверждается.
как
Это
как
просто
бы.
отдельно, вот мы пока не очень понятно зачем, но мы рассматриваем диагональное представление фундаментальной группы. So let me repeat that. In English, we have two groups. One of them is the fundamental group of the boundary of our three-dimensional manifold, which is z squared. And the other one is the fundamental group of the manifold itself, which we do not know yet. But we know that there is a homomorphism from the fundamental group of the boundary to the fundamental group of the manifold itself. Yeah, and up to now we can describe easily diagonal representations of the fundamental group of the boundary, which are written, which such a representation is defined by two non-zero complex numbers, L small and M small, as written on the whiteboard. Okay.
Yeah, and we can see that under so we have a mapping T from R of M to X of M is again we okay, so it is the representations of phi1 of M, and here we have their characters, and here it is like take and trace. Yeah, taking the trace, and we can see that T of R delta of dm is in generic point it will be a twofold covering in generic point. Why? Because we see that it is like, what do we need to solve? We need to solve a plus 1 over L equals something x, L, I don't know, z equals z. In L it is like a second order equation which is generically has two solutions. Okay, sometimes they can coincide. For example, when z is equals 2. Okay. Let's go further. Now we'll introduce our main player. So dm of what when we take the two representatives. Yes, so the construction was dependent on taking two representatives. Okay, so what is it? Is okay, for each I forgot the word, not incompressible, but irreducible component of X of M. So we have a variety of characters. There we have irreducible components. I will say what it is. We take that so what do we need from the irreducible components? For each irreducible components x prime of x of m, or of character variety of m, such that what how did we say it? We we want such that its restriction R to D of m is one-dimensional, we take so we closure of its restriction. We restrict our character to the boundary. Our component to the boundary. We take its closure, and then we take this this preimage under T diagonal. Okay, so when we have a diagonal representation, we could also take it trace, and we just we name it T diagonal in order to understand like in what for what representations we took a trace. And this is the union is dm. The union is of such things is dm of lm. Okay, so what can we say immediately, even before we know when we know something else, that this thing is one-dimensional, because we took a preimage of something one-dimensional under the twofold covering. Yes, so again we have something one-dimensional, and then we also want to work not in the like we want to say that this raw diagonal is given by two numbers L and M. So we say that we say that it is isomorphic to the invertible complex numbers times invertible complex numbers. Yes, again, because L is not 0, because we need to have L to the power -1, and M is not 0 also. So we have a curve, a one-dimensional curve in C star times C star. And now we want to introduce our A-polynomial. Okay, do I need to say about irreducible component what it is?
Not yet.
Okay.
Let's try to understand what's written here. Значит, пока не очень понятно, в частности, потому что тут плохие обозначения. У вас буква М большое обозначает две разные вещи. Она обозначает многообразие, и она обозначает меридиан.
Ну да.
Различать их поэтому трудно. Вот в индексе у D M большое это многообразие, а в аргументе это меридиан. Значит, давайте забудем пока про неприводимые компоненты. Мы берем, можем пока предположить, что у многообразия X от M одна неприводимая компонента. Мы предполагаем, что ограничение характера, да,
на границу одномерно.
Одномерно. То есть L, означает ли это, что L маленькая и M маленькая рационально зависим?
Сейчас, ну, что... Ну да, видимо. Ну, то есть одномерно значит, что действительно у нас, если есть, если мы знаем одну координату, да, то, ну, другая, действительно, у нас все в алгебраической геометрии рационально как-то зависит. Вторая зависит от первой как-то, да. То есть если мы знаем характер на L, то мы знаем характер на M.
Видимо, нет все-таки. Вы хотите, чтобы это была зависимость алгебраическая между числами L и M, да? Вот это вот.
Ну да, да.
То есть у нас есть...
Собственно, полином будет вот, ну, про эту зависимость.
У нас есть... У нас параметры L и M должны быть алгебраически зависимы между собой. То есть они лежат C со звездочкой на C со звездочкой. C со звездочкой нарисуйте только C как комплексную прямую.
Ой, да, точно. В статье она жирная просто,
Ну,
да, поэтому. Но мы правильно делаем.
Вот, у нас есть произведение комплексной прямой без нуля на себя, такой двумерный, то, что называется двумерный комплексный тор. Вот. Значит, координата в первой прямой это L маленькая, координата во второй прямой это M маленькая. И между L и M должна быть какая-то алгебраическая зависимость. Они должны, есть какой-то многочлен от L и M, который зависит только многочлен от L и M с комплексными коэффициентами. Okay, so we restrict, at this moment, we restrict ourselves with such characters, for the variety of characters of our manifold M that are restricted. When restricted to the boundary, the dependence on L and M, they are algebraically dependent, so that we have some polynomial connecting L and M, which means that we have some algebraic curve in the plane C star times C star. Okay.
Yeah, and now the main player, so dm of lm is given by as zero locus of some polynomial which is called A-polynomial of L and M. On.
Can you please repeat what is R of X prime?
R of what? R of x prime. Okay, so we have a representation of we have a character of, so we first we live in space of characters. It is characters of representation, so it is like elements, and to elements of fundamental group, yeah, we assign traces of some representations. Yeah, we look then we restrict ourselves to the boundary. So it means that we take only elements, elements from pi1 of the boundary. And again, the same representations, yes, they're character. We don't need to know the representation. In fact, yes, we know the characters, and we look just the values of the characters only on the elements of pi1 of m, which are also which came from pi1 of dm, okay?
Это ограничение на
So
границу.
да, смотри, у тебя есть функция, ты ограничиваешь ее на подмножество.
Ну да, я понял, просто
Да.
я определение не увидел.
Ну только ограничиваешь, ну смотри, dm, оно вкладывается в m, конечно, но P1
обратно
от
может
DM, оно
не
не вкладывается, потому что там, ты, типа, вот когда у тебя не узел, у тебя там, ну, у тебя L уходит в тождественно, это просто отображение. Ну, вот это отображение есть образ, да, вот у тебя есть образ P1 границы, но вот ты на него ограничиваешь
Ну да, я понял, спасибо.
твой характер. Вот, ну и смотришь, должно получиться одномерно. Одномерно — это значит, что, ну и правда, у тебя между двумя параметрами, вот этими L и M, зависимость. Yeah, okay, so we have some dependency of L and M. Dependence means we have some polynomial, which is whose zero locus is precisely our dm of Lm. But we, of course, we need to say some words here, because we have, if we have like x minus y equals 0, we may write also x minus y to the power m equals 0. Yes, the locus of zeros will be the same. Yeah, x equals y, because we have like here complex numbers, no zero divisors. Of course, if some power of something equals 0, then this thing equals 0. But of course, what we need to have, we need to just we have all the prime factors, yes, so like prime factors are taken to the power 1, okay? So prime factors, linear factors are taken in the first power. Okay, and of course we then can multiply to some invertible number, but this is the like a polynomial is defined up to multiplication to some element of again C star, some non-zero complex number. Okay, so this is like the middle part of our talk, because we have introduced the main player, a polynomial. Okay, so if you have some questions, something is not clear, please ask now, because like it is really the main player.
Could you repeat, please, how we construct a polynomial? Obviously, how can we see what it is?
Oh, I think that like it is hard to see. It is not that obvious in arbitrary case, but we can have some very good example, and it is a very good exercise. So we have unknot, да? Yeah, we have an unknot, and so we want to compute its a polynomial. So not it's like the a polynomial of a knot will be like a polynomial, of course, of S3 minus the epsilon neighborhood, small neighborhood of our knot. Yeah, where when we have L and M are longitude and meridian. Yeah, so what we want to say also that you remember that when we take longitude and meridian, we wanted their orientations, yes, to be like defined up to simultaneous reverse of them. And we see that if we like reverse simultaneously reverse the orientation of L and M, what we do? We reverse L goes to L minus 1, M goes to M minus 1, but their traces are the same. So really, we have the same curve, yeah? So we can, we don't need to bother about the precise orientations of L and M. Okay, so what can we see? So what will be, we have some representation. Then we restrict it to the representation, we take some representation of fundamental group of M. We restrict it to boundary. So will it be one-dimensional in like almost every case? Why it will be one-dimensional? Do you remember what we said about longitude? So what will be the image of a, we can draw it like this. So here this will be the meridian, and this will be, let's draw it like this, the longitude. So what will be the image of the longitude inside of M? Will it be non-trivial? So M is a complement to the open neighborhood of K. Yeah, we want to take open neighborhood because in the complement we want to have the boundary included.
Она будет окружностью.
Yes, it will be a circle, but as an element of pi 1 of M, what it will be?
0.
Yeah, it will be 0 because just this disk, we can contract it along this disk, yeah? Okay, is it okay? And this, and the meridian, of course, will be non-trivial, yeah? Okay, so because it is linked with linked with our knot. Okay, so what can we say about the representation? So the restriction of character to the boundary. To the restricted to the boundary, it will be how it will act on L capital. By what it will be? What will be the R of say chi act? So chi is a character from what? From M So it maps phi1 of m into complex numbers. The restriction, we have an inclusion of dm into m, and we have, so here we have mapping of fundamental groups. Here we had a chi. Here we have a r chi, because like when you have functions, they map in the opposite direction. So when we take a value of restriction on some element of dm, of fundamental group of dm, we would do what? We map it into fundamental group of m, and then we take its character. So what will it be? We have L in pi1 of dm. To what element it is mapped in pi1 of m? It is mapped to an identity, yes? If
Yes.
someone follows me. Yeah, and where does the identity?
Двойку.
Yeah, so it is. It should be mapped to 2, because it is under any representation it is mapped to identity matrix. Yeah, and it is mapped to 2. Okay, so it is mapped to 2, and then we need to take t delta to the power -1, and what do we have? So we have a preimage under this mapping that takes a matrix to its trace. So what do we have? We have an equation L plus L equals 2. It is L squared plus 1 equals to L. So what is L? Okay, L is -1, okay?
Nope. It is +1.
It is, yeah, sorry, it is +1. Sorry, it is +1, yeah. But there, what will be an a-polynomial in this particular case of let's draw it like this, unknot. So we remember that we see that for each for every, when we're talking irreducible components, for everything L equals 1. So their defining polynomial is L minus 1. Okay, so.
А куда m подевалась?
Ну, смотри, у тебя плоскость. У тебя некое множество, у которого всегда L равно единице, да? Одномерное.
Все, я поняла,
Ну
да, мы
вот.
ее стянули, да.
Ну вот, да, оно задается уравнением L-1. Ну а дальше, почему меридиан можно послать куда угодно? Ну, на самом деле, конечно, ну вот нужно как-то, ну то есть меридиан не стягивается, поэтому его действительно можно послать куда угодно. Правильно?
Важно не только, что он не стягивается, но и что любая степень его нет. Нету никакой зависимости. Свободный параметр.
Ну да. Ну то есть он образует там фундаментальную группу, да. Ну да, ну и поэтому, да, в представлении, разумеется, да, у нас нет никаких на него условий. Куда угодно можем его послать. Ну окей, в общем, вот, окей, so this is S for n are not. Okay, so further,
Давайте я еще одно слово скажу, что вот кривая задается уравнением от переменных L и M. В данном случае уравнение это имеет вид L равно единице. Вот. То есть это уравнение прямой, M любой, а L равно единице. Вот это, нас интересуют разные кривые, которые так можно получить. Миша. Нет, опять не ответил. Хорошо. Ладно, продолжай.
Okay. Okay, so let's go further. What we'll say next. So for more complicated knots, the polynomial will be more complicated. A polynomial will be more complicated, but their main theorem of their article was that main theorem of the article in which the a polynomial, I suppose, was introduced, of Cooper, Culler, Gillet, I don't remember how it's written, maybe like this, Long and Shalen, is that boundary slopes are boundary slopes, and I will say what it means. Okay, so what are, like, there are two objects here. The first object is boundary slopes, and the second object is boundary slopes, and the statement is they are equal. Let's say what they are. So the first boundary slope. So we have two a polynomial. We can associate, and it's Newton polygon, да? Yes, we associate. It's Newton polygon, and it has it is something like what is a Newton polygon? Okay, I don't know if I have to rewrite this. Maybe people. Okay, so we take non-zero elements of sum of L to the power I, M to the power J, some coefficients C, I, J, where I and J, yeah. So for all pairs I and J such that Cij is not equal to 0, we mark a point in Z squared. And then takes a convex hull. Okay, so if we have, say, we have Lm plus 3 L4, then plus 8 LM3. So what points we need to mark? Lm, it means 1, 1. L to the power 4, should be 1, 2, 3, 4. This point, and then L and M cubed, it will be this point. And then we have a convex hull of this points. Here it is just this triangle, but in arbitrary case it could be polygon, some polygon. And then it has slopes. Okay, so its edges has some slopes, which are defined, you know, as tangents of like angles to the horizontal line. Okay, so slope is a tangent of alpha, where this is a horizontal line. Yeah, just naive way. And the other boundary slopes are what? And the other boundary slopes are more complicated. So boundary slope, we have an incompressible surface. Is a surface S in M such that it has no non-trivial compression disks. So what a compression disk is? So we have a surface compression disk D.
Саша,
И, да.
может быть, сейчас лучше сформулировать какие-то утверждения про многочлен.
Ну вот это основное утверждение, что...
Это основное, окей.
Да, то есть основное утверждение статьи, что вот у нас, ну то есть многочлен, где здесь приходит, ну вот многочлен, у нас есть многочлен, у него есть полином, этот многогранник Ньютона, у него есть вот эти вот наклоны сторон. Да, вот, то есть явно как бы построено по многочлену. Причем надо заметить, что, ну, это не то, чтобы все, что можно из него извлечь, но сами коэффициенты, они-то определены с точностью до умножения на ненулевую константу, да, ну, то есть, конечно, они, ну, между ними есть еще какая-то, ну, какой во сколько раз чего больше, но вот многочлен Ньютона такой хороший инвариант, многогранник Ньютона, извиняюсь, вот, ну и вот у него вот у всех его сторон есть наклон. То есть сторон-то примерно, да, сколько вершин граничных. Вот. Ну и то есть получается довольно богатая такая информация. И вот сейчас мы увидим, что ну, а нам все-таки мы вспоминаем, что мы хотим что-то понять. Well, we remember that we want to think about topology. Yes, topology of M. And so incompressible surfaces are really powerful, you know, they are used in the definition of Haken manifold. So if we want to say that a manifold is not like very simple, we want to say that it has non-trivial, some non-trivial essential incompressible surfaces. So we'll do the definitions. Yeah, so compression disk D in M is for in M for C, for S is D such that D intersection with S, with our surface, is the boundary of our disk. Yeah, of course it is S1. So what we have? We have some surface, and then we have some disk. Okay, my drawing is not very cool, but so the disk, which is again intersection with S, is the boundary of a disk. They intersect along the boundary circle of D. And what we want to say, of course, for each surface, we have, if we have it as like small part of a surface, like what is the definition of a surface? Is that to manifold, we locally, of course, we can attach such a disk. But what will be it will be very trivial. Yeah, again, if we throw the boundary circle of D, will bound again a disk inside of S. Yeah, so it is not interesting, but it is non-trivial if it doesn't bound a disk in S. So D compression disk D is non-trivial if it doesn't bound a disk in S. Yeah, so why do we care? So again, we have S, we have the definition of compression disks. There are always trivial compression disks, and non-trivial is when it doesn't bound a disk. And incompressible surface is a surface that we have no such non-trivial compression disks. Because why do we want this? Because if we have something like some trivial manifold, and we want to invent something, some complicated surface, we just can attach a handle to a surface. Yes, but then we will have, if we throw out the disk and attach a handle, then we can again glue a disk back, and it won't bound a disk, and we can throw this complicated part and glue a disk back. So the surface was complicated not because of the manifold, but because of we just made it complicated. And we want the surfaces which are complicated by themselves, which are complicated because the manifold is complicated. Okay, so and then what for these incompressible surfaces, they somehow their boundaries. We want to look at the surfaces such that the boundaries are inside the boundaries of our manifold. Okay? And the boundary of our manifold is torus. And in torus we have like two generators, L and M. And we have a coordinate. So ds is, when we thinking up to homotopy about it, it will be some AL plus BM, yeah? And the slope, the boundary slope of S, again, it is like we have a vector with coordinates A and B, its slope is B over A. So it could be infinity. So again, it is a slope of something, just the angle, yeah? And we say that this slope will be equal to the slope of the edges of Newton polygons. Of edges of Newton polygon. So, and it is the main theorem of the article. And to prove it, they use valuations in the function fields over the curves So they are really use of very, at least for me, very advanced algebraic geometry, some stuff from there, yeah. But the results could be formulated on purely like combinatorial and topological language, which is like usual for our seminar, yes.
Sorry, can you please repeat what is B and A?
Okay, so you have a surface inside of M, incompressible surface. It is, we want that its boundary is inside of boundary of our manifold. Okay, so it looks something like this. You know, it is you have surface is two-dimensional, its boundary is one-dimensional, and it is a curve inside of DM, inside of a torus. Okay, and the curve inside of a torus, we can say that in homology, its homology class is a like sum of the homology classes of longitude and meridian. Yes.
Yeah, I understand now. Thank you. That's okay.
Yeah. And but moreover, we can just draw it if we have here like z times z. Yeah, you know, the lattice of homologies. We can just draw this vector, and it's we can write formula that its boundary slopes is b over a, but we can just think of it geometrically. Yeah, so it is some angle, and in Newton polytopes, again, it is polytope in Z2. Yeah, and their boundaries, the slopes of its edges are exactly the slopes of all possible slopes of representatives of DS. Yeah.
А этот многочлен, он может таким образом отличить неузел от узла?
Так, сейчас не узел от узла. Ну, сейчас, ну давай посмотрим, например, вот что у нас было. У нас был не узел, да, вот для него мы посчитали наш многочлен. Он оказался L-1, да, но, к сожалению, у многочлена... нет, стоп, L-1. И что? У него прекрасно есть... Давай посмотрим на... Вот тут есть координата L, да, но она по горизонтали у нас, наверное, пойдет. И есть 1, это что? Это 0,0, да? Ну вот, прекрасно. Есть такой, по крайней мере, сейчас. А есть какая-то несжимаемая поверхность. Ну вот, в самом деле, если у нас есть вот этот вот диск, затягивающий L, то это несжимаемая поверхность. Правильно? Правильно, да? Нельзя ее сжать. Ну, потому что там она, в принципе, это диск, да, там все хорошо. Ну и вот давайте посмотрим на наклон этой поверхности. Но он в самом деле, ну, в гомологиях эта поверхность. So, okay, very, very nice question, very nice example. If we have an unknot, what will be, it is a polynomial is L-1. What is it? It's Newton polytope. Its Newton polygon, sorry, is consists of two vertices 0, 0, which corresponds to 1. Yeah, because 1 is L to 0 and M to the power 0, and 1, 0, because L to the power 1, M to the power 0, and an edge between them. Its slope is 0. Yeah, angle 0, its tangent is 0. Then we have what incompressible surface do we have? Okay, these disks for which L is a boundary is an incompressible surface. You can see it because like any compression disks is trivial because it will bound. Yeah, disk is it is just a disk, our red curve. So this incompressible surface its boundary is L. So in coordinates, it is just ds is L. So it has coordinates 1, 0, and again, it is the slope of this vector is 0. So yeah, they are parallel, this edge and this vector. Okay, so this is a very good example. Прояснила ситуацию, я надеюсь?
У меня немножко другой вопрос был. И, по-моему, ты здесь перепутал L и M, потому что раньше у тебя граница вот этого диска обозначалась буквой M. А теперь это вдруг стало L.
Нет, сейчас, подожди. Граница этого диска, это все-таки у нас L, это у нас longitude, и longitude, он шел по узлу всегда. Ну, longitude всегда был длинным и вдоль узла, поэтому L. Никогда граница диска M не была. Правильно? Правильно.
А слышно ли меня?
Вот сейчас слышно вас.
Сейчас слышно. Хорошо. Я прошу прощения, у меня что-то потерялась зум-связь, и я вас слышу, но не вижу.
Сейчас.
Неважно.
Угу.
Можете ли вы написать еще какие-нибудь примеры А-многочленов для каких-нибудь узлов?
Ну, так сходу не могу, но могу сейчас статью открыть и написать. Да, но так сходу... ну, сейчас, там в статье есть просто, да, какие-то вычисления. Сейчас я могу открыть и...
Okay, I'm asking about other examples of A-polynomials for some other nodes, not just the trivial knot.
Yeah, so let's have a look. Let's have a look. Так, сейчас. Okay, so, yeah.
A very short question. So your polynomials are inhomogeneous in general, right?
Ну да.
Yeah, it's true.
Can you explain? I just missed because you had x minus y to the power n there, and it looked as if it should look homogeneous.
X to the power x minus y to the power n, it was just an example that we want when we define a curve, we don't want the powers of linear factors, because any power will give the same, as a zero locus will give the same the same set. So we just, for any linear factor, we want a first power. It was just an example of how we define a. So it's not, it is x, y are not any parameters that we are caring about.
Thank you.
Okay, so yeah, for other nodes, if we have a PQ torus node, non-trivial PQ torus node, then AKLM is divisible by, okay, I can write it, like if K is a non-trivial is divisible by LM PQ plus 1. Okay. That's it for the examples. Yeah, and in the appendix they have some diagrams, but I don't understand what they mean. So, yeah, not very much to say here. And I suppose that in general it is a complicated task to count this polynomial. So they are talking about that it is divisible by something, but I don't see precise computations here.
Okay, now other examples. So Misha, are you here? Миши все равно нет. Okay. Thanks, Sasha. I hope that at some moment Sveta Gavrilova will explain us a relationship between A-polynomials and cluster algebras, which is a subject of our second seminar. And,
у нас в следующий раз выходной, то есть через 2 недели получается.
Да.
Хорошо.
Yeah, that's what I was planning to tell. There will be no seminar next week because we have a lockdown, lockout, or whatever it is. Some gap in our study plan, and also a Russian state fest. Okay, see everybody in 2 weeks.
Я, а вот можно сейчас там вот я должен для академического резерва сделать демонстрацию своих каких-то там планов. Вот можно,
Да,
наверное, сейчас
давай,
перерыв
давайте,
сделать?
да.
Так,
Давайте.
сейчас я немного, в общем, те, кто хочет послушать, можно уходить, разумеется, но кто хочет послушать, сейчас я немного перестроюсь у себя на компьютере, открою эту презентацию, кину ее в чат. Сейчас. В общем, семинар, наверное, уже закончен, да, но у меня есть
Да.
такой другой. Сейчас я его найду. Так, сейчас нужно запись этого точно остановить. Сейчас, где здесь? Так, все, остановили.